material, pedagogical material presented to us, and or we retrieve the PDF files and then put it on the website.
Okay, thank you. Thanks for being here. I realized by looking at the eyes of some of the students that not everybody was doing physics yesterday evening. But we'll continue now with the second lecture. So the second lecture is on geometrical band theory. It's really the core of the lecture. And if you want to access the lecture note, the address is very long, so I don't write it, but it's easy. In Google, if you type iCubes and then you go in teaching, you will easily find the lecture note. This was a previous school. Okay, so today the plan is there are 5 sections, but it's really in 2 blocks. So the first block is about applying topological ideas, but to band theory. So I will first recap band theory, review the Berry phase in the context of band theory, and then show you that the object that is appearing, the geometrical object, is a fiber bundle, which is called the Bloch subbundle. So there is this notion of fiber bundle in the context of band theory. And then, as an application of this idea, we'll retrieve the quantum Hall effect, but in a very peculiar way, because you will see in this derivation of the quantized Hall effect, there is no magnetic field. Yeah? It will just be an effect of band theory. And it goes in 2 steps. Adiabatic pumping, and then it's very short to get the anomalous quantum Hall effect. Okay, and the following lectures, as I already said, will be 2 concrete examples, 2 concrete models in which we get this kind of effect. First, a topological insulator that breaks time reversal symmetry, which is the Haldane model. It's a variation on the graphene. And then a topological insulator that does not break time reversal symmetry, but requires the introduction of a spin-orbit coupling on the honeycomb lattice. And this is the Kane and Meller model. Okay, so let's get started. So the review on band theory, or the recap, it's mainly to introduce some notation and to point out some subtleties of band theory. So we consider single electron, Hamiltonian, and we are in a lattice. There is a invariance under a discrete translation of a Bravais lattice. And the first object I want to introduce on top of the Hamiltonian is the Bloch Hamiltonian. So the Bloch Hamiltonian is some transformation of the Hamiltonian, single electron Hamiltonian. It's a unitary transformation, and the important thing to notice is that it involves the position operator. So I stress that by putting a hat. This one is also an operator, but it's obvious. So here I want to stress that K is a parameter and R is an operator. And when you do this transformation, this is called the Bloch Hamiltonian. And it's important to realize that this is not exactly the same as the Hamiltonian. It's particularly obvious if you're using tight binding model, because this guy knows about which orbital is connected to which orbital. But quite strangely, this guy does not know at all about where the orbitals are located in real space. But this guy knows. So somehow, if you're using a tight binding description, the information content of this operator is not exactly the same as this operator. This one knows where the orbitals are, and this one may not know where the orbitals are in a real space. And this will play an important role. So then, when we have a Hamiltonian which has the symmetry of a Bravais lattice, we can use Bloch theorem to diagonalize it. So you all know that the eigenvectors and the eigenvalues, they are usually written like this. And an important property is that the band energies, they have the periodicity of the reciprocal lattice. So they can be defined only in the first Brillouin zone. And n here is the band index. It's a discrete, it's an integer. And k is continuous, it's a wave vector in the first Brillouin zone. So this one, continuous in the first Brillouin zone. And the first Brillouin zone, that's a nice thing to convince yourself. It's always a torus, even when it doesn't look like a torus. So for example, for graphene, the first Brillouin zone, the usual one has the shape of a hexagon, but the opposite sides of the hexagons are identified. If you fold it properly, you will realize it is indeed a 2D torus. And actually, it's a general property. And this one is discrete, so maybe I start with 1, 2, 3, etc. Band index. Okay, so these are the Bloch wave function, but those are not the main players. Usually, and this is the content of the Bloch theorem, there is a part which is a plane wave, and then there is a part which lives inside the unit cell, and which is called the cell periodic part. These are the U's. And I will use this strange thing that here I really treat these guys as quantum numbers, band index, wave vector. But here, just to remind, and you will see that this plays a role, that k has a different status from n in the following, that I will distinguish the two. I will keep on treating n as a quantum number, but I will start treating k as a parameter. Actually, as a parameter that I can tune, that I can drive via an external force. To remind that, now I write it like this. Yeah, k suddenly will start having different status, which is that of a parameter and no longer a quantum number. And the property of these guys is that they are, so now if I need to really write the function, if I take it with position bra, then I get the property that these guys, they are periodic, but they are periodic in real space with the Bravais lattice vectors. So these are called cell periodic Bloch function. And in the following, these guys will be the main players. And actually, you can write an equation that looks very much like the first one. It also each k point, you get a Hilbert space, which is a one-dimensional complex Hilbert space. If you have two bands, then it's more complicated. It's two-dimensional complex vector space, etc. Yeah? So the fibers now, they will be themselves Hilbert spaces. Okay. So that's the introduction. Now let's have a look more specifically at Berry phases, because we will see that the way geometry enters is via Berry phases in the context of band theory. And the main idea, so it goes back to Berry, but actually there is a better reference to learn about that. It's also by Berry, but it's 5 years after. And the paper is actually called The Quantum Phase 5 years after. And I recommend reading the second one, because it's more general. It actually shows the full geometrical structure, including Berry curvature, but also the quantum metric. Okay, and the main idea contained in this paper is that in the dynamics of a Bloch electron, there is a separation between two timescales. There is a fast dynamics and there is a slow dynamics. And because we will see that there are these two different timescales, we will ask about some effective description of how the slow degrees of freedom, they evolve when you don't want to see what happens with the fast degrees of freedom. So we'll get the geometry out of the following step. Instead of considering the full problem of a Bloch electron in the presence of an external force, we will restrict to something less general, which is what is the response to an external force of an electron restricted to a given band and integrating out the fact that there are transition to other bands. So the fast motion is the transition to other bands. The slow motion is the motion within a band. And if you want to see these two time scales, we can estimate them. So the slow, or Berry calls them heavy dynamics, is the dynamics within a band. So it's the fact that how long does it take to go from one k value to another k value under the influence of an external force such as an electric field. And you can estimate this time scale. So between 2k value in a 1D model for a finite chain of length else, you have this. And this gives an estimate of the energy, which is roughly h bar times the typical band velocity times delta k. This is roughly the hopping amplitude times A in a tight binding model, where A is the lattice spacing. And this is this quantity. So therefore, this is roughly on the order of T, which is the hopping amplitude, not the time here, times the lattice spacing divided by the total size of the system. And this energy scale you convert to a time scale just like this. So it's 1 over T, L over A. This is roughly the number of sites in the system. And now the fast dynamics is not the dynamic within one band, but it's the possibility for an electron to go from one band to another. Because typically a property of a band structure is that you have several bands, not a single one. And the dynamic now is cut between what happens as a function of k, what happens as a function of n. If you want to have a clearer picture, you can imagine that band structure is a bit like endowing the electron with something like the structure of an atom. It still has the orbital motion, that's k, but now it starts having internal levels. These are the bands. And the dynamics, internal dynamic in real space, it's what happened in the unit cell, it's fast. And the slow dynamics is how you move from one unit cell to the next one. You also see it here. plane wave is from one unit cell to another. It's the slow stuff. And the U's, it's the fast stuff within the unit cell. And there you can also estimate the typical energy. So now, typical energy is at fixed k, you go from here to here. So it's typical to either a bandwidth or a band gap. So it's typically on the order of t. So now the energy here of motion, it's typically a bandwidth or hopping amplitude. And therefore, the corresponding time scale is typically 1 over, h bar over t. And now, because of course n is large, you see that this time scale is much larger than this one. That's why this one is slow and this one is fast. So that's the main message of Berry. I can recast it like this. What we're after is the reaction of the light system or the fast system. So system here means faster degrees of freedom would be better. The reaction of the fast degrees of freedom on the slow degrees of freedom. And this happens through an emergent gate field. And this emergent gauge field is all the quantities that carry the name of Berry. So it's Berry connection, Berry curvature, integral of Berry curvature, which is called the Chern number. It's also the Berry phase. So it's the appearance of something that looks like a gauge field, a bit like electromagnetism, but it's in K space, and it's not God-given, but it's emergent through the fact that the electron is moving in a periodic potential, which separates the dynamics into what happens within a band which is slow and what happens between the bands which is fast. So what we are after now is the description of projection of the dynamics within a single band, integrating out the virtual transition between the bands. And the effect of this virtual transition will be to modify the naive semi-classical equations of motion for an electron within a band with extra terms. And those extra terms, they are typically Berry curvature, orbital magnetic moments, and all those terms, you will see they are related to this guy. And that's how this geometrical structure is appearing. Okay, so now let's do the original calculation of Berry, but in the context of bands. So what we want to study is what happens to an electron in a given band that I prepare in an initial state, and then I move it slowly in a parametrically slow way. I start from an initial state which is in a given band, so n now will be fixed, and in a given k0 state, and I want to change the k value of this electron very slowly. So here is the Brillouin zone, here is my starting point, k0, and I'm in the third direction, you have the energy bands, and I'm restricting to the nth band. So you imagine a band structure. I only look at one band, and I want to move slowly the electron on a trajectory, changing its k value that I will see as a time-dependent process, but which is slow. And I want to adiabatically follow the electron while it's staying in the same band, and I want to perform a closed loop in reciprocal space. And the question that Berry asked and answered is that the adiabatic theorem in quantum mechanics tells me that if I'm moving very slowly, I will stay in the nth band, because this band is protected from the other ones by gaps. So if I'm slow compared to h bar divided by the size of a gap, I will not have real transition to the other bands. And the question he asks is, when I come back, do I end up in the same state as the initial state? Or do I end up in the same state up to a phase? And actually the surprise is that there is, or there might be a phase related not to real transitions which are forbidden, but to virtual transitions to the other bands. So the Berry phase effects is really related to restricting to a band and seeing what happens because of virtual transition to the other band. If you take a very simple tight binding model with a single band, then you don't get any of these effects. To get this type of effects, you need the fact that the Hilbert space is larger than only the band you're looking at. So in nature, there are always several bands, but in models, you could be working with such a simple model that there would be a single band. In such a case, there are no Berry phase effects, etc. The dimension of... So there are things which go through any dimension. So you also get part of these effects in 1D. But some of the effects do not go trivially. For example, the Chern number, it's for 2D bands, not 1D, not 3D. Then you can again define the second Chern number for 4D bands, etc. But so there are restrictions. But in 1D, there are some other interesting phase, which is called the Zach phase, which do not exist in 2D. Yeah. So there are differences between dimensions, but the general stuff for the moment is pretty similar. So Berry asks, Adiabatic theorem tells me I should remain in the same state or in the same band, but just changing my k of t. So k of 0 is k0. And then I'm driving myself. I'm really taking the electron by hand or putting an electric field that I control, which is small enough that I do not make real transition to other bands, and I follow this path. The adiabatic theorem tells me at first approximation I'm staying in the same state, but it's not forbidden to have the same state in quantum mechanics, means up to a global phase. Berry asks, can I compute this guy? Is it interesting? So the answer is yes, you can compute it. It's not very complicated. You use the dynamics that is correct for the electron, which is the Schrödinger equation, time dependent. So you solve this equation, and h of t is actually the Bloch Hamiltonian in which I'm controlling the way k moves. And I'm solving this equation by plugging in this ansatz. That's what Berry did. Yes. Yeah, sorry. There'll probably be a lot of h-bar missing. Oh yeah, oh yeah, and there is one point which I forgot to mention, is that now I'm working in the n's band, so I restrict to a basis made of these guys. I fix n, and k is in the first Brillouin zone. And this basis is called the adiabatic basis. And it has the property that it needs a choice. Somebody else could have chosen an alternative basis simply by choosing a different phase. So the relation would be something like this. And this choice of phase in the basis, it's now a gauge choice, and it's called the Berry gauge. So in the literature, it's often just called the gauge choice, but I want to attract your attention to the fact that it's not the electromagnetic gauge. It will also be a U1 gauge, just a phase. It's just a phase because I'm discussing the case where I restrict to a single band. But I could decide to restrict to 2 bands. I have 10 bands, I restrict to 2, I remove the other ones. I project on those 2 bands, and then the phase would be more complicated than the phase. It would be a small unitary matrix of dimension 2 by 2. Here it's a unitary matrix of dimension 1, so it's U1, but it's not the electromagnetic gauge. So I call it the Berry gauge. So there is a choice. Somebody else can do another choice. It's equally valid, but all the physical results you should end up getting, the things that are measurable, should not depend on that choice. So then you will see that this distinguishes in those quantity those that are measurable and those that are not. We'll see that the Berry connection is not measurable, but the Berry curvature is measurable. Just like the vector potential in electromagnetism is not measurable, but the magnetic field is measurable. So this is the U1 Berry gauge. Okay, so we make a choice. We have our exact equation. We make this ansatz. This guy is a function of t. I can solve for it. So I skip one step, but basically you get gamma dot of t equal minus n k of t. Oh, this is me? No. Sorry. Plus k dot scalar. I should not have put the microphone near my ass, but okay. Okay, yeah, that's it. So there are two steps that I do not write here, but I'm sure you'll be able to do it. You can find the equation for gamma of t. You see there is one phase which is not a surprise. If you integrate this phase to get gamma and not gamma dot, you just get the integral over t of the energy, and that's called the dynamical phase. But then there is some surprise. There is an extra term which is related to the u-ends. And this is called, this term, it has a name, it's called the Berry connection. And it's A, or curly A, because it's very similar, we'll see it's very similar to a vector potential. So when we integrate that, we can integrate between 0 and the final time where I close the loop. And then I can decide that the initial gamma is 0 by convention here. And then I get the integral over t between 0 and final time of the energy. So it's a dynamical phase. You're used to that for a eigenvector. The dynamical phase is the energy of the eigenvector times the time. Here, because it's adiabatic following, the energy is changing a little bit during the motion, therefore you get an integral, but basically it's energy times time, plus an extra phase, which is an integral over k. It's a line integral of the Berry connection, and this integral is now, you see, written like this. This is k dot, so it's dk over dt, and I multiply by dt. So the time goes away, and now it looks like an integral that does not depend on time, and it's on a closed path, because I decided to ask the question, what is the final phase compared to the initial phase? And this is the Berry phase. And you see that it has a structure very similar to an Aharonov-Bohm phase, only happens on a closed path. Otherwise, it's hard to define the meaning of the phase if you don't have a reference phase. And it looks like the curl, or the line integral of a vector potential. But now it's not electromagnetic vector potential, but it's Berry vector potential, which is called Berry connection. It's emergent and due to the band structure. So at this point, you may have the impression that this only involves the n bands and has nothing to do with having other bands. But that's actually not true, because you can show that this expression, if you have a single band, it's 0. here? No, I just, no, you just need that it has, no, actually, there are almost no, you don't even need it to be periodic. Yes. Yes, this comes from the fact that h of k, this comes from this structure, that h of k is linear in the, this is the transformation. But you don't need to assume much on this guy. The extra terms come from this and this. Okay, so this goes under other names. It's also called the geometrical phase, or it's the anholonomy that I mentioned. So holonomy is the fact that you perform a cycle and you come back to exactly your initial state. This is a holonomy. And here it's called anholonomy because you come back not exactly on the same state, but you have a difference in phase. Okay? So the picture of this is that imagine now that at each point in k-space, I draw the phase of the wave function. I draw it as a line, but actually it should be a circle because the phase is u1. So it's not an infinite line, it's a line modulo 2 pi. So at each point here, your fiber now is a u1 fiber. It's where it's your phase, but it's simpler to draw as an open line. So imagine this is an open line going like this, like this, like this. Each point in k-space, I have a phase, and I'm following the phase. At first it's 0, then it's something else, it's something else, something else, something else. And I move and I follow the phase. And when I come back, the surprise is that, of course, I'm back to the same un, because by construction that's what I assumed, but I'm at a different altitude on my fiber. And the difference in altitude on the fiber, this is the Berry phase. Okay. Okay, so let me introduce some more notation on the Berry phase, and you will recognize the analogy with the electromagnetism. So the Berry phase is the equivalent of the Aronoff-Bohm phase. The vector potential is now called the Berry connection. It depends on the closed path, and it depends in which band you are. And if and only if the Berry connection is well defined over the complete patch over which I'm moving, which may not be the case. There are cases where the Berry connection, you cannot have a smooth global gauge that works in all of Brillouin zone. But if we assume that on the path this is the case, then I can use Stokes theorem. And if I can use Stokes theorem, I can transform this into a two-dimensional integral over the curl of the Berry connection. And the curl of the Berry connection, it looks like a magnetic field, and it's called the Berry curvature. So, and maybe a better notation would be a curly B, but okay.
So in this contour you have a pre-index n. So does this, but you do it on the left-hand side. So does this imply that different bands have got the same?
No, it should be a function of both the path and the band. Yeah. And this Berry phase is basically the flux of Berry curvature across the surface which you encircle in k-space. But note that this is very important, the fact that you have a smooth global gauge, which means your Berry connection is well defined over the whole set, because precisely when this is not true, then we'll get the equivalent of a magnetic monopole, which is called a Chern number, non-zero Chern number. This is because this guy, it's a phase, so it's defined modulo 2 pi, and all the subtlety is what is the value of the integer times 2 pi. Is the integer 0? this is zero magnetic monopole or zero Chern number, or is it a non-zero integer? The reason, if the Stokes theorem works, the reason that the Berry phase is zero is that imagine that you take a very particular path. The origin of the Brillouin zone doesn't matter, so I could draw now the Brillouin zone where K0 is on the corner. Imagine I take a very particular path. I encircle the full Brillouin zone. But when I encircle the full Brillouin zone is a torus. So actually the path that I'm drawing, it's also the null path. I'm doing nothing. So on the null path, the phase should be zero. So if you take the Berry phase for the full Brillouin zone and Stokes theorem is valid, the flux across a path that encircles an area which is zero. So the only way out of this argument, the only way to get not zero but 1 times 2 pi or 3 times 2 pi or something like this, is that this doesn't work. And this is that's why I mentioned the Dirac magnetic monopole. That's the main idea, that getting a non-zero Chern number, the Chern number is precisely the Berry phase but computed on the full Brillouin zone. Having a non-zero Chern number means that there is an obstruction to finding a smooth global gauge on the whole Brillouin zone. If you don't need patches, like a convention in this area of the Brillouin zone and another convention in the other part of the Brillouin zone, you don't get a non-zero Chern number.
You said the Chern number is only valid in 2D?
Yes.
What changes then if you go up to 3D?
In 3D, there are no Chern numbers. So this was a part of the excitement about discovering the Z2 topological insulators of Kane and Meller, is that they existed in 2D, just as the quantum Hall effect, but surprisingly they also exist in 3D, whereas the 3D quantum Hall effect does not exist. Again, in 4D, you get another variation of the quantum Hall effect, but not in 3D. Okay, so I'm skipping a bit because lunch is important, so I'm skipping a bit the details of derivation, but now you have my scanned notes, so I give you more details there on the calculation. There is one important expression for the Berry curvature that I would like to give, which shows that the Berry curvature is not a property of a single band, but involves the presence of other bands. So yeah, I should just write the name. So this is the Berry curvature, equivalent of the magnetic field, but in K-space. This is the Berry connection, equivalent of the vector potential in K-space. This is the Berry phase. It's the equivalent of the Aronoff-Bohm phase, but in K-space. And the equivalent of the Dirac magnetic monopole, it's called the Chern number. And it's defined like this. Yeah, this is me again. Sorry. It's the integral of the Berry connection for the Berry curvature for a given band, but on the full Brillouin zone. And the Brillouin zone, now I'm restricting to a 2D Brillouin zone, so it's T2. And this is basically 1/2 pi times the Berry phase, but computed on the full Brillouin zone. And therefore, this should be an integer, because I divide by 2 pi. Can be 0, can be non-zero. And the important thing to remember is that can only be non-zero if there is an obstruction to finding a smooth global gauge for the Berry connection. Because the Berry connection, just like the vector potential, it's a quantity that is gauge dependent. Whereas the Berry curvature, like the magnetic field, is a quantity which is gauge independent. So the expression that I want to give of the Berry, so I should first write the Berry curvature in 2D, the simple expression where I simply take the curl of the Berry connection is like this. partial derivative with respect to kx of the un, partial derivative with respect to ky times un, and then the complex conjugate. And this guy, here it seems to involve only the ends band, but actually you can show that the gradient of un, should write it, the gradient of un, if you want you can write it like this, it's actually in first order perturbation theory, it's easy to show that this quantity, and there are the details in the note, is actually a sum over all other bands of the following expression. And all quantities are computed at the same k value. You recognize the structure of first order perturbation theory where the perturbing operator is the grad of k, and you see that this is only non-zero if there are several bands, and it involves transition between your original band and other bands. Because of this, there is an expression which makes more physical sense of what the Berry curvature is, and it reads like this. You use this expression for this guy and for this guy, and you find that the Berry curvature, it has the structure of second order perturbation theory that you will probably recognize. It has two matrix elements for transition between the band in which you are and another band, and then you come back in your original band, and the price you pay to do this is related to the energy difference between the band you start from and the energy at the same k value of other bands. The only thing that seems strange for second order perturbation theory is the exponent 2 here instead of 1. But otherwise it has this structure. And for me, what this means is that the picture I have in mind is the following. When I want to restrict to the ends band and I want to describe the electron, when it's at a given k value, actually the dynamics of the electron in this band, it's not only about naively projecting on this band, but it also involves this type of quantities, which are virtual transition to other bands. Not real transition. The probability of finding the electron is always 1 in this band in the adiabatic approximation and 0 in the other band. It's not Landau-Zener tunneling. It's virtual transition. But those virtual transitions, they are modifying the effective dynamics of the electron in this given band. Yes?
So what would happen if you had degenerate bands?
If you had?
If you had degenerate bands.
Oh, so then happens what I mentioned at the beginning. If you have degenerate bands, it means you restrict to a pair of bands. If you restrict to a pair of bands, you get similar emergent gauge structure, but instead of being a U1 gauge structure, it's going to be a SU2 gauge structure. And then it will not be like electromagnetism. It will more look like higher gauges.
Okay, so where have we assumed in this previous treatment that we're...
Yeah, I didn't say it, but I assumed that this band is non-degenerate. So I looked at the projection on a single band.
Okay, but where in this derivation is this?
Oh, it's because here you see I'm proportional to a single state and not to a linear combination of 2 or 3. Okay. So I erased the plan of the lecture. So now the third step of the first block is that I want to show you to wrap up a little bit all this and see why this has the structure of a fiber bundle. But the main message is that from Berry, that this type of physics, it's not restricted to band theory. It's all over physics. So actually in the paper by Berry, he takes the example of the Born-Oppenheimer approximation, where you have electrons and nuclei. The nuclei are slow, the electrons are fast. He wants the effective dynamics of the nuclei in presence of the fast electrons after integrating out the fast dynamics. Here it's a different context, but we also have the same idea. You have a quantum system that splits into something fast, something slow. You want to know the slow dynamics and how it's influenced by the fast dynamics that you integrate over. Here the strange stuff is that the fast and the slow, they are both related to the electron. And the fact that you have fast and slow comes from the band structure. Slow is virtual transition, slow is within a band, fast is between the bands. Yes?
Before I had a chance to raise this, I mean, this is not very marked, but maybe you would highlight this, and maybe it would be nice to see. The top equation doesn't depend on any n prime, it just depends on n.
Yes.
And yet, when you write down the last equation, the fast involves the sum.
Yes.
Could you explain how that's possible? Where does it come from?
Okay.
Because if you have a single band, then eventually your Chern number is 0.
Yes. Okay, so where does that come from? It comes from the fact that, so I will show it now. It comes from the fact that actually the gradient of un, it's not simply something proportional to un. It's actually when you take un at k plus dk minus un at k. This is so this is a dk grad k un, and this here it looks like first order perturbation theory. So this is the zeroth order, and I want to know the first order, and the perturbation is proportional to dk. So if you look at the Hamiltonian, it's h at k plus dk, and this I write as h of k plus dk grad k of h. So this is my zeroth order Hamiltonian. This is the eigenvector. This is my perturbation. And the perturbation, it happens to be not diagonal in the un prime basis, and therefore you get these guys. So and then probably here you recognize first order perturbation theory. Yeah, so indeed this is puzzling. If you don't look at this expression, if you only stay here and here, you may have the impression that it involves a single band, and then you say, okay, what's the fuss about having other bands? Yes. But we'll now see that the crux is again what I mentioned at the beginning, that these guys, the UNs, in a single band, they are not orthogonal. So it's a basis, but it's not orthogonal. They have overlaps. Okay, so I'm at point number 3, the Bloch subbundle. Okay, so the first point is what I mentioned before, this idea that you separate the degrees of freedom into fast and slow, and you want to know the back reaction of integrating out the fast degrees of freedom onto the slow ones. Want to know the dynamics restricted to a single band, but including the fact that you know virtual transitions are possible to other bands. The Hilbert space is larger than just a single band. And why does this come about? It comes from this fact that even if you stay in the same band, this scalar product, when k prime is different from k, is not 0. Actually, this comes back to my initial point, that this is not a standard eigenvalue equation. It's an eigenvalue equation, but k is no longer a quantum number in this equation. It's a parameter because it appears in the Hamiltonian. So for the k value, this guy is an eigenvector with this eigenvalue. For k prime, which is different from k, I have a different operator. This guy is an eigenvector of a different operator. Therefore, there is no reason that those two are orthogonal. But if I'm not changing k, but changing n, so now I stay at the same value of the parameter, But now n is changing. Those two guys are eigenvector of the same h of k, and they correspond to two different bands, and therefore those are orthogonal. So the non-trivial stuff is this one. So I have a adiabatic basis, this u n k for a given n and varying k, but this basis is not orthogonal. And because it's a scalar product in a Hilbert space, this is a complex number. And because it's a complex number, there is some interesting stuff appearing that could involve either the phase of this complex number or the modulus of this complex number. So the phase of this complex number, it gives rise to all that I described here: Berry connection, Berry curvature, Berry phase, and Chern number. But there is also some interesting stuff related to how the modulus of this complex number evolves in k-space. And this is the quantum metric. So it's less studied, it's less famous, but there is also some interesting geometrical structure appearing because of the modulus. So here I just write what I wrote before: Berry connection, Berry curvature, Berry phase, and Chern number. 4 quantities related to the way the phase of these guys evolve when I move k prime away from k. The first 3 ones, they are geometrical quantities. The last one is truly a topological quantity. Those, they exist locally in k-space. This one is not measurable because it depends on the gauge choice. These two are measurable. And this one is a global quantity. It involves integrating the Berry curvature over the complete Brillouin zone. And it's usually 0, except if you have an obstruction to finding a small global gauge over the full Brillouin zone. Just like magnetic monopoles in real space are possible only if there is an obstruction to finding smooth vector potential all over space. You remember yesterday the crucial point was we could study a magnetic monopole, but the price to pay was that we had to introduce 2 patches. Because if we took a single patch, then we were not studying a magnetic monopole, we were studying a solenoid, infinitely thin, but cut somewhere. It looked very much like a magnetic monopole, but actually the flux entering through the solenoid, it was radiating out from the end of the solenoid, and the total flux across a closed surface was 0, because what was entering was going out. So the only way we could simulate or have a magnetic monopole was to have 2 patches. Here it's similar. This guy only exists if there is some obstruction to finding a smooth global gauge. I should say a word so that it's less abstract. What does it mean, an obstruction? It means that when you're computing, when you're doing a concrete calculation, this guy is a vector with several components. If I have 5 bands, therefore I have 5 components. And choosing a gauge is usually I decide that my first number, I don't want it to be a complex number, I want it to be real. Okay, I fix this is my gauge convention. I get this guy to be real. But there are band structures for which this choice is not possible all over Brillouin zone. Because you move in the Brillouin zone and you encounter points where this guy vanish. And when this guy becomes 0 at a given point, you can no longer tell what's its phase. And because of that, you need 2 patches. You need a patch around the point where this goes to 0 and a patch for the rest. And this is a case where you will have an obstruction to finding a smooth global gauge, and that's how you get a Chern number. Yeah? Okay, and so this is the phase, but there is also an interest in how the modulus evolves, and how the modulus evolves gives rise to another geometric quantity, which is called the quantum metric. It has been less studied. It's also interesting. I know less about this guy, and in particular, I don't know the analogy in electromagnetism. to me, this does not exist in electromagnetism, or if it exists, then it's probably a flat metric, not very interesting. But I just want to show you the definition. It's also involving gradients of UN, and it's also appearing in some physical quantities, such as the orbital magnetic susceptibility. But now people are studying this. It's appearing in many quantities. So how do you define the quantum metric? You start by defining something like a distance between quantum states. And the distance between quantum states is you look at how the overlap between two neighboring UNs evolves as a function of their distance. And this, you force it to look like a metric that depends on two indices and that depends on, on dki, dkj. So this is the quantum metric. It's the way it is defined. You see it has the structure of a metric like in special relativity, for example, except here there is not the time involved. It's only kx, ky if you're in 2D. And the information it contains is about the way the overlap in modulus of two UNs depends on dk. So it's a distance in Hilbert space. And some people are studying also if there is some topological thing involved in relation to the quantum metric. Here it's a geometrical object, but from a metric, if you know well relativity, it's obvious you can compute the Riemann curvature. From the Riemann curvature, you can also define some topological invariant, such as the Euler invariant. So there are people studying these kind of things. But I won't say more, just want you to remember that the crux is these two guys not being orthogonal, and therefore there is something happening because of the phase of this complex number, and also something happening because of the modulus of this complex number. Okay, and now I want to make the connection with the fiber bundle language. So after projection on a single band, I don't discuss the case where it's degenerate, you get the appearance of this fiber bundle where the base space is the Brillouin zone. It's a special base space because it's compact, it's a torus, and it's also called sometimes the projective Hilbert space. And I think of it as being the parameter space. And what is the fiber? The fiber here is the remaining Hilbert space at each value of the parameter k after doing the projection. So if you don't project at all, at each point in k space, you have a Hilbert space which is number of bands. If you have a problem with two bands, you have a Hilbert space with two bands. If you project, you can get less bands. So the fiber is actually, in the case that I mentioned, it's basically, or roughly speaking, the phase of UNK at fixed n. So in our case, it's a one-dimensional Hilbert space. And the fiber bundle at order 0, it's the cross product of the base space and the fiber. But now you know that when you do that, it could happen that the gluing on an object which is compact, that is closed, it could be non-trivial. So in general, it's not, it's the product, cross product of B cross F when the Chern number is 0, and it's not that when it's non-zero. Actually, the Chern number, it was invented by Chern as a marker to tell you whether the fiber bundle is trivial or not. When it's 0, the fiber bundle is trivial, and E is simply B cross F. And when the Chern number is non-zero, it means this is not true. It's more like a Möbius strip. But an abstract Möbius strip, because the base space is the Brillouin zone, it's a torus, and the fiber, it's not simply a segment, but it's itself a one-dimensional Hilbert space if you project it on a single band, or it could be a higher Hilbert space if you have a degeneracy and you project it on 2 or 3 bands. Yes?
I understand this is a mathematical construct, but what does it like physically mean to have a monopole in the field?
Okay, so my understanding is the following: is that the magnetic monopole. Okay. So this is a very interesting question. Somehow the answer was already found by Berry, but it took me a lot of time to realize it was already in his paper. Is that we are studying a band insulator. The bands are well separated. And the Chern number, it characterizes a full band. I can say this band has Chern number 1 and that band has Chern number 0. What does it mean that a band has a Chern number which is non-zero? It means that there is a magnetic monopole somewhere. But the magnetic monopole, actually, in the context of band theory, is related to band touchings. And then you don't understand. You say, okay, I'm studying cases where I have gaps. I have a Chern number, and he says Chern numbers are related to magnetic monopole, and magnetic monopole, they correspond to band touchings, conical band touching. What's the connection? Do I have a gap? Do I do not have a gap? Actually, it means that your Brillouin zone is a torus. So imagine a donut. If you move on the surface of the donut, that's physics. This is parameter space. You have bands, you have gaps. But now you extend your theory. You do something like analytical continuation, and you want to define something that happens in a third direction, which is moving inside the torus. If you start moving inside the torus and defining your band structure, now no longer as a 2D band structure, kx, ky, it's the surface on the torus. Imagine you have kz now, which is like filling the inside of the torus. And when you have a non-zero Chern number, it means that inside the torus, when you move in this third direction, then you have a band touching. Because when you add one direction, you deform your band structure, and you may close the gap, or you may not close it. So the case where you have a non-zero Chern number, it means that in this third direction, which is entering the inside of the torus, you actually have a band closing. Yeah? So what I want to mean is that there is a relation between physics in 2D and physics in 3D. Because there is another context in this business of topological band theory in which you will hear about Chern number. It's either bands in 2D, as I said, or it's also in the context of Weil semi-metals, which are band touching points in 3D. Some of you may have studied Weil semi-metals. It's the 3D equivalent of graphene. It's conical intersection, but in 3D. And those conical intersections in 3D, they are described as topological defects, and they are characterized by a topological charge that you compute on a sphere surrounding this defect. And this topological charge is also called a Chern number. And actually, those two concepts, those two situations, gapped 2D and band touching 3D, they are related by what I just mentioned, the entering of the inside of the torus, adding a third dimension. So the So the way you do it is that you introduce a third parameter in your Hamiltonian by hand. You start varying the hopping amplitudes by a new parameter, and then this new parameter you interpret as a kz, and then you study a band structure in 3D between two bands, and you look for gap closing and band touching in this new setting. If there is a band touching, it means you will get a Chern number. So it's a bit, I agree, it's not obvious connection. But there is so magnetic monopole, it's actually conical band touching, but in one dimension higher. So one way of seeing this connection is that when you have, imagine you have a model where you have a parameter to study a phase transition between one Chern insulator and another Chern insulator, and the transition goes through a gap closing, and then it reopens. This parameter that you tune to go from one gap situation to another gap situation via gap closing, this is your Kz parameter. And your gap closing is now like a vial semi-metal in 3D. Yes, of course. And any parameter that tunes the phase transition, pressure. Yeah, it could do it. But it should be a field that only does this job and does not destroy the band structure. So if you have a 2D system, you apply the magnetic field like this, you lose the band structure because it becomes Landau levels, etc. You need to put the field in the plane or something like this. Okay, so my last point here is that here we have a fiber bundle appearing, and the Chern number is the topological invariant characterizing this fiber bundle. So it is a marker that tells you whether the fiber bundle is trivial or non-trivial. Just like a number that would tell you if you are in the situation of a regular cylinder or if you are in the situation of a twisted cylinder, which is called a Möbius strip. So here it's a bit more abstract, but it's the same idea. But notice that this topological invariant in this context, it's not here associated to a topological defect with the cage, etc. Here it's associated with the fiber bundle that lives globally on a compact space, which is the Brillouin zone. But still there is a relation between those two notions, as I just mentioned. There is a relation between having a twisted fiber bundle in 2D and having a topological defect in one dimension higher by introducing an extra parameter that closes the gap. Okay, so now I'm late, and I'm switching to the fourth part, so it will be probably quite sketchy. The fourth part is application of this idea. I want to, the final aim is to show you that even if historically the quantum Hall effect was discovered via the application of a magnetic field, and apparently had nothing to do with band structure, it was discovered like this, and it took very long time to understand actually that the quantum Hall effect, the most natural way to describe it is it's just an effect of band theory. So the historical steps is experimental discovery, 80s, then Taoles, Komoto, Nightingale, and Denise, who understood that the whole conductivity could be related to a topological invariant called the Chern number. But somehow in their construction, it was still with a magnetic field. So they had a tight binding model, put a magnetic field, you get an energy spectrum which is known as a Hofstadter butterfly. They were studying the Hofstadter butterfly. They realized that in the Hofstadter butterfly, you could define topological invariants. Actually, it was already there that what they were doing was studying band theory, because in the Hofstadter butterfly, if you're familiar with this, at some specific fluxes, which are rational numbers, the Hofstadter butterfly, you can compute the structure. It's again a band structure, but it has a higher number of bands. The number of bands is related to the flux. If the flux per plaquette is P over Q, you get Q bands in a magnetic Brillouin zone. So somehow there was a relation, but nobody really understood that it was there. So the one that understood that is a Haldane. So Duncan Haldane, 88, he makes the next step completely removes the homogeneous magnetic field and actually shows that you can have a band structure for a band insulator that carries a Chern number and therefore a Hall conductivity. Yeah, so that's what I want to show quickly, that you can understand the quantum Hall effect as being an effect of band theory for a special kind of band, a band that carries a Chern number. So for the moment, if you want, we have done geometrical band theory, and now I'm switching to the topological part, the part where there is something interesting coming from the global structure of this fiber bundle and not just locally. Okay, I need to cut a little bit short in the story. So I will actually start from the semi-classical equations of motion of an electron restricted to a given band. So in the notes, I'm skipping about 2 pages, which is a derivation of these equations. Now I'm just giving the equation and showing the consequences. So if you want to look in the derivation, you can follow it. It's not a full derivation, because I never found a nice way to do the full derivation, but it captures some of the terms that are new in the semi-classical equation of motion, namely the one which is called the anomalous velocity. So the idea here is that we have known for many years, actually since Peierls and Bloch, what are the equations of motion for a Bloch electron in a given band. They look very simple, natural, and familiar, but actually it took many years to realize that they were wrong because some terms were missing. So these are the textbook equations, for example, in Ashcroft-Mermin or in Kittel. Goes back to the 30s. It tells you something that seems very natural. Velocity is group velocity. And the first equation looks like Newton's equation, where momentum is changing in time because of an applied force, and the applied force is electric field and magnetic field. Those equations, they look innocent, but actually they are quite hard to derive, even at this order of approximation. And actually they are wrong. They are wrong in many cases they do work, but they are missing terms. So what we want to do is to have the correct equation at linear order in the external fields. So the terms which are missing, it took a long time to get them. The first term which was added to that comes from Karplus and Luttingers in the 50s. It's called the anomalous velocity, and it's a term that comes here. And it involves the Berry curvature. So this is the term that I derive in the notes, and here I shortcut directly to the result. And you see it looks very much like a dual to the Lorentz magnetic force. Instead of the magnetic field, you get the Berry curvature. And instead of R dot, you get K dot. Because this is magnetic field but in K space. This is magnetic field in real space. The other modifications, so now it will start looking messy on the blackboard, is that the first equation you can rewrite like this. You can rewrite as a gradient in real space of a modified band energy. And then something like that looks like the Lorentz force, but with a new position operator. So you will see that this guy, R, curly R, there is no accepted notation. So this is just my own notation. So don't stick to it, but it's not the same as this one. And this is related to, you remember, because of electromagnetism, we know that there is a difference between canonical momentum, P, and gauge invariant momentum, pi. This is because of electromagnetic gauge. But now we have a new gauge on top of this one. We have the Berry gauge coming from the band structure. But the Berry gauge, it lives in K space. Therefore, the minimal coupling, it's no longer on P, it's going to be on R. So now we'll have an R which is canonical, and we'll have an R which is gauge invariant. So the curly one is the gauge invariant one. So the curly R, it looks like this plus the Berry connection. Just like the gauge invariant momentum, it's the canonical momentum plus the vector potential. So this is the usual difference between the thing which is gauge invariant and the thing which is canonical. And now we get the same also for position. So one way of thinking of the Berry connection is that it's changing the meaning of position in real space. Why is it changing the meaning of position? Because canonical position only knows of your position in the sense of in which unit cell are you. But it doesn't really tell you what's happening inside the unit cell. So this guy is playing this role. So the other modification, so now in the equation of motion, it should be the gauge invariant quantity appearing. And the second equation now is like this. And the modified energy, now energy is, it's semi-classical, so it's an energy that depends on momentum and position. It's the band energy. And there is also a scalar potential. When I will take its gradient with respect to R, I will get the electric field. And there is also, so this is pretty standard. This is the energy of the band. This is like introducing an electric field, but via a scalar potential. But now I get an extra term, which I didn't talk about today, which is also one of these Berry quantities, which is called the orbital magnetic moment. It also depends on the band, it depends on K, it has a big expression, very similar to the Berry curvature, and it actually has the feeling of a Zeeman effect, but an emergent Zeeman effect. Maybe you haven't noticed, but I never talked about spin. I was considering spinless electrons. Didn't discuss about spin for the moment. But here you have an emergent spin. You have like a Zeeman effect, but where the magnetic moment is not related to the real spin and to the gyromagnetic factor, but it's related to the band structure. So I just quickly give the expression of this orbital magnetic moment. How you compute it is actually very simple. You compute something like orbital momentum, but of self-rotation. So the average means expectation value in the U and K state. Here it's the position minus the average position. So actually so the physical picture behind this is the following. If you try to make a wave packet for an electron restricted to a given band, because a band has a finite size in energy, it means it cannot be infinitely small in real space because of Heisenberg uncertainty relation. If you squeeze in energy space, you need to spread in real space. Therefore, your wave packet, it has a finite size, a minimal size, just like the Compton wavelengths in the Dirac equation in high energy physics. Your electron, it's a wave packet, but it cannot be as narrow as you want. It has a finite size. Because it has a finite size, on top of its motion for the center of mass, there is also a possible motion which is self-rotation. And this is the magnetic moment related to this self-rotation. If you compute this, you get the following expression, I E divided by 2h bar, and then it looks very much like the Berry curvature, sum over n prime. It has the two matrix element of the velocity operator. So now I'm writing in the forbidden zone, but I'm reading what I'm writing, so should be okay. It's the velocity operator.
Can you switch back to white? It's really hard to see the black.
Yeah, sure, sorry. But the new terms are blue. Pedagogy goes first. No, I'm just kidding. So it has the same expression as the Berry curvature, so you can just recopy the previous one. The only difference is you get a power of 1 instead of a power of 2. Otherwise, it's the same up to the prefactor, and then you need the complex conjugate. The derivation of this equation, the full one, having all terms at linear order in the external field, because if you want to go to second order, you get extra terms. It goes, it belongs to Chan Nu. So if you want to see a nice review, you look at the reviews of modern physics 2010. The derivation is actually very hard to follow, but these guys were, at least you will get the correct final expression. And in my notes, you will get the correct derivation, but only of this term. Yeah, but that's the one that I need for the 10 minutes before lunch to show you quantum Hall effect. So this one is called the anomalous velocity. It dates back to Karplus and Luttinger. And it's quite natural. It's a dual of the Lorentz force. It's due to the effective magnetic field, but in K space. And this one, that actually will enter in the gradient here. No, sorry, it disappears from here, but it will modify something here. Gradient of K of this will give a term. It will give like a Stern-Gerlach force, but coming not from the fact that the magnetic field depends, has a spatial inhomogeneity, but because the magnetic moment depends on K, and therefore in grad of K it will be non-zero. So the way to think of this is emergent Zeeman effect. Actually, this may seem completely out of nowhere, but you actually already know an example of that. If you think back on your Dirac equation, your beloved Dirac equation, if you remember going from 3 + 1 Dirac equation to the Pauli equation in the slow velocity limit, have you done this kind of derivation? When you do this, the Dirac equation, it has 4 bands. 2 bands at positive energy, 2 bands at negative energy, they are degenerate. In the Dirac equation, there is no spin. If you look at the equation, there is no spin. There is no Zeeman effect in the Dirac equation. When does the spin and the Dirac and the Zeeman effect appears? It's only when you take the slow velocity limit and you project on the 2 upper bands and you obtain an effective Schrödinger equation for the 2 upper bands, but with a main novelty is that it's a Schrödinger equation, but there are 2 bands, degenerate. Therefore, the wave function is not really a scalar, it's a spinor. And in addition, you get the Zeeman effect with the G factor being equal to 2. So this is exactly the same mechanism here. We are projecting the dynamics onto a restricting number of bands. And when doing this, there is the appearance of an orbital magnetic moment or Zeeman effect. Yes? Okay, so let me finish with the anomalous quantum Hall effect. Now we have all the ingredients. Okay, so now I want to answer the question: can a 2D band, which is filled, conduct electricity? So the textbook answer is no. This is the reason for having a band insulator. If you have a system with two bands and your Fermi level is here, the textbook answer is that there is no conduction, a field band does not conduct, and you may remember the reason. It's not that nothing is happening, but it's more like half of the electrons going that way and the other half of the electrons going the other way, and the currents, they exactly compensate, and you do not carry a total current. Okay? But okay, let's try with our new equation. When you do this transport calculation for a field band, you don't have this term. So now we want to see the answer when we add this term. So I consider a case with an electric field, but no magnetic field. So what is the current carried by the ends band? It's occupied. It's the electric charge minus E, 1 over the total area of the system. Sorry for the notation. Now it's the area, it's not the Berry connection. You sum over all states in the Brillouin zone for this band, and each state I want to know its velocity. And its velocity I read here. Velocity is now group velocity and anomalous velocity. The group velocity, it's precisely the term that is usually present, and the group velocity, it's the term that because the, okay, I should write it, because the energy band are periodic with the Brillouin zone, when you compute this, you get 0. I'm using this equation now, but putting B to 0, no Lorentz force, no orbital magnetic moment. I'm putting an electric field that enters here, and the only term in the first equation is h bar k dot is minus E times the applied electric field, and the second equation is r dot, the velocity, is the group velocity plus the anomalous velocity. This term goes to 0 by the usual argument that a field band does not conduct. But now I have a second term, and the second term, it looks like minus E integral over k divided by 2 pi square over the full Brillouin zone. This is all this. And now I put the velocity, and the anomalous velocity is minus k dot cross the Berry curvature. But minus k dot, or k dot, it's just minus E electric field divided by h bar. So this guy, it's electric charge, electric field divided by h bar. And now you may see the structure that I have. The only thing that depends on k is the Berry curvature. All this goes in front. The curl, the cross product goes in front. And what appears is the integral of the Berry curvature over the full Brillouin zone. And that's the definition of the Chern number. So if I write the current carried by a field band, I have the surprise that it's not 0, but only if the Chern number is non-zero, and that it's given by the following expression: E square over h, the Chern number. Chern number, it's integral over all k of the Berry curvature, and there is a 1 over 2 pi. So one of them stays there, and the other one goes in front and combines with the h bar to make h. And here it's electric field cross UZ. So now you see you have a current, but you apply an electric field like this, and it's a whole current, first thing. So a full band can have a whole current, and in addition it's quantized because the Chern number is an integer. So I will stop here. This shows that a field band in a band insulator can conduct electricity, but only in a whole way, transverse, and in a quantized way. But of course, there is one thing that I didn't show is now I need to prove that there are band structures for which the Chern number is non-zero. Here I didn't prove it. This result is also correct if I put 0 here. Yeah? So next time we'll see the Haldane model, which was the first concrete example in which you have a band structure with bands carrying non-zero Chern number. Okay, let's eat.